Hello students, hope you are doing fine. Today let us go into the subject of power electronics, and I would guide you in analyzing the operation of one of the most commonly used power converters, that is an inverter. So inverter is a device used to convert DC power into AC power. Inverters are broadly classified into two types, that is based on the type of supply used, which are three-phase and single-phase inverters. In industrial scenarios where high power applications are involved and drive-based systems are operated and automated, three-phase inverters play a pivotal role in controlling the operation of the drives, thereby controlling the production level. The three-phase inverters make use of two modes of operation, which are 180-degree conduction mode and the 120-degree conduction mode. Today we will be discussing on a three-phase inverter operating in 180-degree conduction mode. Here you can see a three-phase inverter circuit diagram. The inverter begins with a DC source, which in industries would be from large size rectifier units. This DC is then given as the input to the inverter as shown here. You have the three-phase inverter, which is also called as the six-step inverter, consisting of 6 switches which can be thyristors, MOSFETs or IGBTs based on the power handling capacity required. 6 diodes are placed in anti-parallel with the switches that are used as freewheeling diodes for protection of the switches in case of a lagging current. Let us consider the switches to be thyristors. The thyristors are numbered in this fashion, that is T1, T3, T5 in the upper group and T4, T6, T2 which constitutes the lower group. The diodes are also numbered accordingly. Now let us have a look at the switching scheme involved to change the DC input to three-phase AC output. Here in the switching scheme you can see that the switching states of different switches are shown. It is to be kept in mind that no two switches of the same leg should be operated together. Here you can see that T1 and T4 or T3 and T6 or T5 and T2 should not conduct together, as it can cause a short circuit. So only after T1 is turned off, T4 is turned on, and similarly once T3 is turned off, T6 is turned on, and T5 is turned on and then it's turned off, and then only you can start with T2. So this follows the pattern. Now moving on to the switching scheme, you can see that this is how the switching scheme is arranged for the inverter. It can be seen from the switching scheme that all the switches conduct for 180 degree. Hence it is called as a 180 degree conduction mode. If the switches conduct only for 120 degree, it is called as 120 degree conduction mode. Also, when we analyze the conduction period between the subsequent switches, it is 60 degree. That is, T2 starts to conduct after 60 degree with respect to T1. Similarly, T3 conducts after 60 degree from T2, and this pattern goes on. Now let us analyze its operation. At the beginning of conduction, switch T1 starts conducting, but we already have T6 and T5 conducting. So now 3 switches are active with 2 switches from the upper group, which are T1 and T5, and 1 switch from the lower group, which is T6. So drawing the resultant connection diagram, we obtain the equivalent circuit as shown in the figure. When we find out the current in the circuit, we obtain it as I is equal to Vs by Z plus Z by 2, which will be equal to 2 by 3 Vs by Z. Now the voltage across the phase A, that is Va naught, is Vs by 3. It will be equal to the voltage across phase C, that is Vc naught, since both the A phase and C phase loads are in parallel. The B phase voltage will be equal to 2 Vs by 3. Since the current is leaving the terminal B, the voltage is taken as negative. So we can conclude that Vb is equal to minus 2 Vs by 3. So now in the first conduction region, the waveforms are marked with the obtained values. So in the waveform you can see Va naught is equal to Vs by 3, Vb naught is equal to minus 2 Vs by 3, and Vc naught is equal to Vs by 3. This gives the phase voltage with respect to the reference point O. The line voltage can also be found out similarly. From the figure, it can be seen that I have marked the three possible line voltages, which are VAB, VBC and VCA. VAB will be equal to VA0 minus VB0. So substituting the values we obtain, it is as VAB is equal to Vs by 3 minus of 2 Vs by 3, that will be equal to Vs. Similarly, the same can be found for VBC and VCA, which are minus Vs and 0 respectively for the first conduction region. Now when we analyze the second conduction region, we find that T1, T6 and T2 are conducting. So now we have one switch from the upper group and two switches from the lower group. So the equivalent circuit we obtain can be analyzed like this. Here when we look at the phases, we have the current entering through the A phase load and leaving through B and C phase loads. So the voltage VA0 will be equal to 2 Vs by 3 and VB0 and VC0 will be equal, which will be equal to minus Vs by 3. The line voltages can be found by doing the same as in the previous case. Here we will obtain the line voltages as VAB is equal to VA0 minus VB0, which will be equal to 2 Vs by 3 minus of Vs by 3, which will be equal to Vs. VBC will be equal to VB0 minus VC0, which will be equal to minus Vs by 3 minus Vs by 3, that will be equal to 0. And similarly, VCA will be equal to VC0 minus VA0, which is equal to minus Vs by 3 minus 2 Vs by 3, which will be equal to minus Vs. This can be implemented for each switching operating region, and you can see that the waveform are taking the shape of an AC. Here you can also see that the waveform representation of the line voltages, which clearly shows that you have converted the DC into an AC. Therefore, we have successfully implemented a 3-phase inverter that will be operating in 180-degree conduction mode. Hope you have got a good insight on the operation of the 3-phase inverter, and now regarding the 120-degree conduction mode, that can be discussed in another class. Until we meet again, bye.